Assalamu alaikum and welcome FBISE chemistry students. Today, we're jumping right into this explainer to clear up one of the most frustrating head-scratching topics in electrochemistry, standard electrode potentials. Specifically, we're going to finally solve the infamous anode mystery.
Okay, so let's just ask the exact question that's probably been bugging you all year. Standard tables give us reduction potentials, but oxidation happens at the anode. So why do we have to flip it? It honestly feels like one of those random rules chemistry teachers invented just to make board exams harder, right? But I promise you, there's a really beautiful, solid logic behind the whole thing. In this explainer, we'll break it down, recovering the anode mystery, the Hill analogy, reversing the sign, oxidation versus reduction, avoiding common mistakes, and then wrapping it up with a final FBISE exam summary.
Let's kick things off with Section 1, the anode mystery.
So the root of the confusion is this. Standard reference tables only show us what happens when electrons are gained. Whenever you look up a value, you are looking at a reduction half reaction. Now this perfectly matches the cathode's job, right? Any reduction takes place at the cathode anyway. So for the cathode, the table is totally good to go, exactly as it's printed.
But the anode, well, the anode is literally defined as the electrode where oxidation occurs. Electrons are being lost, not gained. Because the anode actually undergoes oxidation in real life, its reaction is mathematically backwards compared to what you see in the textbook table. That mismatch is exactly what forces us to reverse it.
But here is an absolute golden rule you have to remember. The actual chemical reaction determines which species is oxidized and which is reduced. You can't just arbitrarily change a reaction because some other metal has a lower standard potential. If your specific reaction shows tin losing electrons, then tin is your anode. The actual flow of electrons dictates the whole shebang. Matlab ye hai, don't change the chemistry to fit the reference table, use the table to understand the chemistry.
Moving right along to Section 2, the Hill analogy.
Think of it like a ball sitting on a hill. It literally cannot roll from the bottom to the top all by itself. Going uphill requires energy, it's non-spontaneous, and in electrochemistry, we assign that a negative value. But going downhill, that releases energy. It happens completely spontaneously and gets a positive value. We only reverse reactions on paper to figure out that natural spontaneous direction. Samajh aage baat?
All right, Section 3, reversing the sign.
This part is actually incredibly straightforward. An electrode potential depends entirely on the direction of the electron flow. So the second you reverse the reaction, like changing it from a reduction to an oxidation, the electron flow flips. And when that flow flips, the sign of the potential reverses too. If you don't reverse the reaction, the sign just stays exactly the same. It's a simple, direct cause and effect.
Which brings us to Section 4, oxidation versus reduction.
Let's look at the core difference here. Reduction potential measures the tendency of a species to gain electrons. On the flip side, oxidation potential measures the exact opposite, the tendency of a species to lose those same electrons. While they're measuring opposite tendencies, they are just describing the exact same chemical relationship, just from two different viewpoints.
Because they represent the identical relationship, but from opposite directions, they are mathematical mirrors of each other. They are completely equal in magnitude, but opposite in sign. So, if a reduction potential for a certain metal is, say, positive 0.34 volts, its oxidation potential is absolutely going to be negative 0.34 volts.
And this right here brings us to the ultimate master formula for your exams. E cell equals E cathode minus E anode. By just putting a minus sign in front of the anode's reduction potential, this equation mathematically does all the reversing for you. You literally just plug in the reduction potentials straight from the table for both, and that tiny little minus sign works its built-in magic to flip the anode's value into an oxidation potential.
To keep everything straight in your head, just follow these two strict steps. Step 1. Use the reduction potential when the species is at the cathode or if the reaction is explicitly written as a reduction. Step 2. Use the oxidation potential when the species is at the anode or if you physically reversed its half reaction on your paper. Stick to those rules and you'll never plug the wrong numbers into your equations again.
Now for Section 5, avoiding common mistakes.
Think of this as your personal pre-exam checklist so you don't throw away easy marks. First, do not use the wrong formula. It is always cathode minus anode. Second, identify your anode and cathode based on the actual reaction happening, not just looking at the numbers. Third, never forget to reverse the sign if you manually reverse a half reaction. Fourth, don't mix up your oxidation and reduction potentials. And lastly, hamesha dhyan rakhein. always pay attention to standard conditions and the current direction shown by voltmeters in any diagrams.
If you want to completely lock this into your memory, I want you to remember this slightly silly but super effective phrase. An ox, lose, red cat, gain. What on earth does that mean? Well, anode means oxidation, which means lose electrons, and red means cathode, which means gain electrons. Honestly, just write this at the top of your rough sheet the minute you sit down in the exam hall.
Let's wrap things up with Section 6, your FBISE SE exam summary.
Here is your absolute biggest takeaway. Once you do your cathode minus anode calculation, take a hard look at the sign of your total E cell. A positive total cell potential means your reaction, just like that ball rolling naturally downhill, will happen spontaneously. It'll generate a voltage completely on its own. But a negative cell potential? That means the reaction is non-spontaneous. It requires external energy to happen, kind of like physically pushing that ball back up the hill.
So you now have all the tools you need to completely solve the anode mystery and calculate the standard cell potential flawlessly. But I'll leave you with a quick thought experiment. You know how to calculate E cell when everything starts out at standard conditions, right? But what happens to the voltage when the reaction finally reaches equilibrium? Does the ball just sit there at the bottom of the hill? Think about that as you review your notes, because understanding what happens when the ball stops rolling will take your electrochemistry mastery to the absolute next level. Best of luck on your board exams. Thanks for hanging out with me.